Welcome back to the video course on fluid mechanics. We were discussing about the turbulent flow. So, we have seen various characteristics of turbulent flow, and then we have seen various reasons for turbulent flow, and we were discussing about the various factors affecting transition flow from laminar to turbulent flow, like free stream turbulence, pressure gradient, roughness of boundary, then curvature of boundary, suction of boundary, etc. And then also we have seen this all these turbulence are caused due to abrupt discontinuity in velocity distribution, generally occurs due to various reasons, and then of course due to the shear flow. So, due to the shear flow there is a mean velocity variation in space, and then that is causing the turbulence. So, further also we have seen that generally the turbulence flow, it is very difficult to solve the problems to find out the velocity distribution, it is very difficult. So, generally practice what we do, we use the say a mean value components for the velocity, and then what happens to the fluctuations. So, that is what we were discussing in the last lecture on turbulence. So, now as I mentioned, the velocities say in 3 dimensions, u, v, w can be expressed as u is equal to a mean value u bar plus u dash, where u dash is the fluctuating component, and this u bar is the mean velocity component. We can write that is equal to 1 by t integral 0 to t u dt, t is the time, and then v the velocity in y direction, we can write v bar plus v dash, where v bar is equal to 1 by t integral 0 to t v dt, and w is equal to w bar plus w dash, w bar is equal to 1 by t integral 0 to t in w dt. So, this we have seen how we are expressing the various velocity components u, v and w, and similar way we can express the pressure and other components with respect to a mean component, and then the fluctuating component or the instantaneous component. So, this we can, it is clear from this figure here. So, you can see that the velocity say in x and y direction u, v, it is represented here. There is a mean value of u which is called u bar here, and then the mean value of v in y direction v bar, and then you can see that we are expressing the turbulences with respect to this mean velocity. So, the fluctuations you can see that it is going up and down due to the various disturbance taking place in the flow. So, these are called the fluctuating components for u and v, and then we will be expressing with respect to the mean component plus the fluctuating component. So, this we have seen the time average of these fluctuations u, v, w are 0. Since we can show, as we have seen earlier, say the mean component of u dash is equal to 1 by t integral 0 to t u dash dt, that can be equated to 0. Similarly, v and w also, and generally we express this root mean square, say u dash bar or square, that used to describe the violence of turbulent fluctuations, and it is generally a measure of intensity of turbulence. So, as we have seen, due to various reasons, it is very difficult to express the real velocity fluctuations. So, generally what we do, we express as a root mean square component. So, you can see here in this figure how we express this root mean square component. So, this is the velocity distribution versus time on x axis and velocity on y axis. So, you can see how the variations takes place with respect to the mean component, and then you can see that here we express in terms of u RMS, that means the mean root mean square of the velocity fluctuations. So, that is also expressed in a other scale. Here u RMS is shown here. So, this root mean square of the velocity is generally used to express the turbulent components in our the various fluctuations as far as turbulent flow is concerned. So, then some of the other important definitions here is say called isotropic turbulence. That means if this mean square velocity fluctuations in x, y and z directions are equal, then we call this the turbulence as isotropic turbulence. That means u dash bar square is equal to v dash bar square is equal to w dash bar square. So, that case we call that turbulence as isotropic turbulence, and then the intensity of turbulence is generally expressed as Here you can see that in this slide the intensity of turbulence is equal to 1 by u infinity, which is u infinity is the free stream velocity, into square root of u dash bar square plus v dash bar square plus w dash bar square by 3. So, this gives the intensity of turbulence. So, this is also an important definition in turbulent flow. And then if you want to find out the average kinetic energy of turbulence per unit mass, we can write as u dash bar square plus v dash bar square plus w dash bar square by 2. So, this is the average kinetic energy per of turbulence per unit mass. So, these are some of the important definitions which we generally use in turbulent flow and its various parameter determinations. So, now another important parameter is turbulence shear stress. So, turbulent shear stress, so we can express as tau x y with respect to t, that is equal to eta du bar by dy, where u bar is the temporal mean velocity. So, we have already seen what is temporal mean velocity, that means with respect to the long time how the variations takes place for the velocity, so and the mean velocity. So, this the turbulent shear stress we can express as eta into du bar by dy, where eta is called the eddy viscosity or dynamic coefficient of turbulence. So, then we have seen that whenever we discuss, say for example, when a flow approaches flat plate. So, you can see here, say let us assume that here there is a flat plate put like this. So, if a free stream velocity as we describe here, say a free stream velocity, say let us assume that u infinity is coming, then we can see that there is a boundary layer is generated. So, initially the boundary layer will be laminar and then it become turbulent. So, this is the general pattern whenever this is the laminar boundary layer and then here there is a transition and then here there is which is turbulent. So, generally when we discuss the shear stress, so here you can see that with respect to the flow is coming and then turbulence is generated after some time for the flow over a flat plate. So, the shear stress, when you consider the total shear stress with respect to this, here you can see in this slide the total shear stress is equal to tau is equal to tau laminar plus tau turbulent. So, as we have already discussed, the laminar shear stress can be expressed as mu into du bar by dy and a turbulent shear stress is expressed as eta into du bar by dy. So, the total shear is equal to mu plus eta into du bar by dy. So, wherever the turbulent flow is present, if there is a laminar boundary layer or laminar component is there or laminar sublayer is there. So, the total shear will be the shear stress due to the laminar flow and plus the shear stress due to the turbulent flow. So, then here as we have seen earlier, so this eta by rho, eta is the dynamic coefficient of turbulence. So, eta by rho is called kinematic eddy viscosity. In turbulence flow we call this term eta by rho, where rho is the mass density, eta is the eddy viscosity or dynamic coefficient of turbulence, that is equal to epsilon, that is called kinematic eddy viscosity. So, actually this kinematic eddy viscosity epsilon is a measure of transporting capacity of the mixing process. So, as we have seen earlier cases, as some of the slides say a lot of mixing takes place in turbulence and generally this eta by rho, that means the kinematic eddy viscosity we can describe as it is as a measure of transporting capacity, that means due to the turbulence and mixing process transport takes place and this epsilon is a measure of the transporting capacity of the mixing process whenever you consider the mixing in the turbulence. So, now before deriving the basic equations of turbulent flow, we will see some of the classifications of turbulence. So, we have already seen the various causes of turbulence and then we have seen the various factors affecting how a flow is changing from laminar to turbulence. So, based upon this we can classify the turbulence into 3 categories. So, turbulence classification we can have in 3 categories. First one is called wall turbulence. So, wall turbulence means the turbulence by viscous effects due to presence of a solid wall. So, here first category is called wall turbulence. So, this is due to the presence of solid wall. So, as we have seen earlier, say some of the other earlier slides, you can see here, say whenever there is the presence of a solid wall, like you can see here in the slide, say here there is a sphere. So, then the flow comes and then turbulence is generated, or with respect to here you can see also submarine is there. So, due to that the presence of solid wall, that case, say whenever the turbulence is generated, that case the turbulence is called the wall turbulence. So, this is one of the important category of say one of the, as we have seen, some of the important reason is presence of solid particle fluid structure interaction. So, this is one of the important category of the turbulence, wall turbulence. Second one is called free turbulence. So, free turbulence means turbulence by fluid flowing at different velocities in the absence of solid. So, in the case of free turbulence, as such there is no presence of say the solid wall or solid material in the flow, or there is no fluid structure interaction takes place, but the turbulence is generated by fluid flowing at different velocities. So, you can see that here, say if we plot say for example, a flow is in a channel like this. So, then if due to various reason, if the say the velocities, say here if it is u1, u2, u3, and then if there is considerable change in velocity, you can see that after some time a mixing starts, and then the turbulence starts due to, say the flow become from changes from laminar to turbulence due to this mixing. So, this region is now turbulence. So, this turbulence which is generated is called free turbulence. So, here as you can observe, there is no specific the reason for turbulence is only between different layers. What happens, that means velocity changes and then turbulence is generated. So, this is called free turbulence. So, and then the third category, so the turbulence can be a mixed effect, that means there can be wall turbulence as well as free turbulence. So, if the mixed effect is there, then the third category is a combination of wall and free turbulence. So, these are the 3 important classifications of turbulence, and based upon which we can say subclassify, and then we can try to analyze various turbulent flows. And now, say now we have seen the classification, now we will see the theory of turbulence, and then we will derive the governing equations of turbulence. So, as we have seen the say in the Reynolds experiments, we have seen that once the flow reaches a critical Reynolds number, the flow changes from say transition takes place and laminar flow become turbulent. So, the value of critical Reynolds number for a given flow, below which what disturbances decay and above which at least some disturbances amplify, is determined analytically by the theory of stability of laminar flows. So, scientists try to analyze this turbulent flow for a long time, and then they compared with the laminar flow, why this turbulence is generating, all this were critically analyzed, and then say they use the theory of stability of laminar flow. So, say in a flow regime, to the flow to be, if it is laminar and if it is to be continued as laminar flow, that is called a theory of that is the theory of stability of laminar flow. So, why a turbulence is created, why there is a deviation takes place from the stability of the laminar flow. So, these various scientists analyzed this with respect to the critical Reynolds number, and they found say the reasons are the various disturbances, and whether the disturbance generated in the fluid system, whether if it is decaying, then the flow become again laminar, but if it is due to various reasons, as we have seen, presence of the solid body or the velocity variation or the the boundary roughness, then these disturbances are amplified, and then the stability of the laminar flows goes, and then flow become turbulent. So, this theory is based on the assumption that a fluid motion consists of a mean flow and disturbance superimposed on it, as we have already discussed. So, this is the theory of stability of laminar flows based upon assumption that a fluid motion consists of mean flow and a disturbance superimposed on it. So, now let us say let the velocities in x, y, z direction, when we consider 3-dimensional problem, let the velocity be velocities be u x, u y and u z, the velocity in x, y, z direction, and p be the pressure component. So, as we have seen, as based upon the theory of this turbulence, we can express the mean flow as say u x bar plus u x dash, and u y is equal to u y bar plus u y dash, and u z is equal to u z bar plus u z dash, and then with the pressure can be written P is equal to P bar plus P dash, where P bar is the mean pressure and P dash is the fluctuating components. So, you can see that all these fluctuating components are generally smaller than the main flow. So, the mean velocity components, say if we consider the velocity components as q bar, this u x dash, u y dash, u z dash, if we consider as q bar, and p bar is the mean pressure component, but we can get by averaging the velocities and pressure for long time. As we have already seen the previous slide, this we can obtain by averaging this velocity components and pressure for long time. So, the mean quantities of the fluctuations are steady, as we have seen the fluctuations takes place, say if this is the mean component, and then up and down fluctuation takes place, and then if you consider the fluctuation for a long time, or you can see that these fluctuations say for a long time it is steady. So, these fluctuating quantities are responsible in producing additional stresses. So, as we have already seen, this the fluid molecules jumps, and then this fluctuation takes place, and these fluctuating quantities are responsible in producing additional stresses called apparent stresses. So, these additional stresses due to the fluctuating component, the stresses, additional stresses produced are called apparent stresses or Reynolds stresses, in addition to the viscous shear stresses and normal stress sigma I. So, in any fluid, as you can see that there is already a shear stress component and then normal stress component, and in turbulent flow, other than this, additionally due to this fluctuating quantities, we have the apparent stresses or Reynolds stresses due to the fluctuating quantities. So, when we analyze a turbulent flow, we have to consider the normal stresses, we have to consider the shear stresses, and then also we have to consider the apparent stresses or Reynolds stresses. So, due to this, and moreover this apparent stress or Reynolds stress are due to the fluctuating quantities, it is also fluctuating, and then it is very difficult to quantify. That is the real challenge in the turbulence modeling. So, now we will go to the general equation of turbulence. So, here we will be trying to derive the general equations based upon the existing theories. So, the governing equations of turbulence flow is generally called as Reynolds equation. So, these equations consists in 3 dimensions, it consists 3 equations, momentum equations and the continuity equations. So, these equations are derived from the general equations of motion for any flow, the Cauchy's equations, by considering the above discussed theory of turbulence. So, the Reynolds equation now we will be deriving. So, these equations are generally starting from the Cauchy's equation. So, we will be discussing in a later chapter on Cauchy's and Navier-Stokes equation we will be discussing, but we will start now to derive this Reynolds equation from the Cauchy's, the basic Cauchy's equation for fluid flow from the general equation of motion. This is the Cauchy's equation by considering the theory of turbulence. So, general Cauchy's equation of motion in vector differential equation form we can write as g minus a into rho plus del p is equal to 0, where g is the acceleration due to gravity, a is the other acceleration components, P is the surface forces. So, this capital P is the surface forces. So, we can see in standard literature the Cauchy's equation, general Cauchy's equation, this anyway we will be discussing it further when we discuss the Navier-Stokes equation also. So, the general Cauchy's equation is actually you can see that with respect to the acceleration components. So, due to gravity and then other accelerations are there and then multiplied by rho plus the surface forces, the variation surface force or del P is equal to 0. So, this is the general Cauchy's equation. So, based upon this we can write the 3 equations of motions for the general fluid flow, and then that equations are transformed into the Reynolds equation by using the theory of turbulence. So, this equation now the general equations of motion, so called Cauchy's equation, we can write as I mentioned, these equations we will be discussing later in the Navier-Stokes equation chapter. So, this equation now in x, y, z component we can write as del u x by del t plus u x into del u x by del x plus u y into del u x by del y plus del u s into del u z del u x by del z is equal to x minus 1 by rho del p by del x plus 1 by rho del sigma x dash by del x plus del tau y x by del y plus del tau z x by del z. So, here as we have already seen u x, u y, u z are the velocity components in the x, y, z direction, t is the time, capital X is if there is any body force, and then P is the pressure, rho is the density, sigma is the normal stress, tau is the shear stress. So, similar way in y direction we can write this equation, the general equation of motion or the so called Cauchy's equation as del u y by del t plus u x into del u y by del x plus u y into del u y by del y plus u z into del u y by del z is equal to y minus 1 by rho del p by del y plus 1 by rho del tau x y by del x plus del sigma y dash by del y plus del tau z by del z, where y is the body force in the y direction, and in z direction del u z by del t plus u x into del u z by del x plus u y into del u z by del y plus u z into del u z by del z is equal to z minus 1 by rho del p by del z plus 1 by rho del tau z by del x plus del tau y z by del y plus del tau sigma dash z del by del z. So, these are the 3 general equations of motion or so called Cauchy's equation x, y, z directions, and then we have the continuity equation. So, if the flow is by considering the density, the continuity equation we can write as del rho by del t plus del rho u x by del x plus del rho u y by del y plus del rho u z by del z is equal to 0. So, now we are going to derive the Reynolds equations based upon these 3 equations of Cauchy's equation of 3 general equations of motion and the continuity equations. So, now say most of the problems, if we consider the flows to be incompressible. So, rho is constant. So, we do not have to consider. So, that the continuity equation number 4, earlier equation number 4 we can write as del u x by del x plus del u y by del y plus del u z by del z is equal to 0. So, this is the continuity equation for incompressible flow as shown in this slide. Then say now we are in the process of deriving the Reynolds equation. So, now the equations of turbulence are similar in form. So, we derive only for x direction. So, as I mentioned, we are now trying to get the equations for 3D flow problem, 3D turbulent flow. So, we will be having 3 equations of motion in x, y, z directions. So, say this and continuity equation we have already seen. So, x, y, z directions 3 equations. So, there were various steps involved in deriving this equation is same either in x or y, z direction. So, now we will derive the equation here in x direction, and then we will write the equation in y and z direction in a very similar way. So, that is the procedure we adopt here. So, now the earlier Cauchy's equation here we have seen that we have got here this convective terms. So, if we consider the equation in x direction, so we have this 3 convective terms u x into del u x by del x plus u y into del u x by del y plus u z into del u x by del z. So, this we will consider to deal with this convective terms. We will be initially considering some specific steps, and then we will be simplifying these terms by using some mathematical approximations. So, here say the convective terms here u x into del u x by del x and u y into del u x by del y, u z into del u x by del z. So, these 3 terms we will be considering convective terms. So, here u x this is u x into del u x by del x plus u y into del u x by del y plus u z into del u x by del z. So, the convective terms we can be better represented by putting them in differentials of quadratic terms such as u x square, u subscript x square, u x into u y, u x into u z as written here. So, that is u x into del u x by del x plus u y into del u x into del y plus u z into del u x by del z. These 3 terms can be written as del u x square by del x minus u x into del u x by del x plus del u x into u y by del y minus u x into del u y by del y plus del u x u z by del z minus u x into del u z by del z. So, in this equation now this is the left hand side is written to the this form. So, now here we can use the continuity equation which we have seen here, equation number 5. So, if we use that, then you can see that this term u x into del u x by, so this u x can be taken out. So, we can write say and then say this term u x into del u x plus del x, and the second term, so this term 3 terms we can combine together. So, this on the right hand side, second term, fourth term and sixth term. So, we can combine these 3 together and then use the continuity. So, it will become null or 0, since del u x by del x plus del u y by del y plus del u z by del z is equal to 0. And finally, this convective terms which is represented as in this equation as in the following. So, finally, we can write this as a convective term becomes del u x square by del x plus del u x u y by del y plus del u x into u z by del z. So, the convective terms in the Cauchy's equation, general equation, is transformed initially in this form by the mathematical say simplifications. So, now finally, this Cauchy's equation or the equation of motion we can write in this form after the changing the convective terms as in the previous slide. So, we can write del u x by del t plus del u x square by del x plus del u x u y by del y plus del u x del u z by del z is equal to x minus 1 by rho del p by del x plus 1 by rho del sigma dash x by del x plus del tau y x by del y plus del tau z x by del z. So, now we will introduce the turbulent and mean terms. So, this is now the Cauchy's, the equation of motion is transformed as in equation number 6. So, now as I mentioned, so we will be now changing this with respect to the theory of turbulence, where theory of turbulence is there is a mean component for the velocity and pressure, and then plus a fluctuating component for the turbulent flow. So, we will introduce the turbulent and mean terms, so that now the equation 6 becomes here del by del t of u x dash plus u x bar plus del by del x u x bar plus u x dash square plus del by del y u x bar plus u x dash into u y bar plus u y dash plus del by del z u x bar plus u x dash u z bar plus u z dash, that is equal to x minus 1 by rho del by del x p bar plus p dash plus 1 by rho del sigma x dash by del x plus del tau y x by del y plus del tau z x by del z. So, equation 6 is changed into equation 6a by applying the theory of turbulence, where the velocity and pressures are expressed in terms of a mean value and the fluctuating component. So, now in advanced mathematics we can, there is a term called averaging the terms, which is defined here. So, the averaging, the rules for time averaging is, say for example, some of the terms is expressed here. If A and B are two dependent variables, then we can time average as given in this equation. A double bar is A bar, A plus B bar is like this. Various time averaging can be done as in standard advanced mathematics test given in advanced mathematics textbooks. So, this time averaging concept we will be using here for the earlier equation, equation 6a. So, if we use the time averaging concept, so we can write by averaging the terms, we will get del u x bar by del t plus del by del x of u x bar square plus del by del y of u y its mean value bar plus del by del z u x u z bar is equal to x minus 1 by rho del p bar by del x plus 1 by rho del sigma x dash by del x plus del tau y x by del y plus del tau z x by del z minus del by del x of u dash x square bar minus del by del y u x dash u y dash bar minus del by del z u x dash u y dash bar. So, this is equation number 7. So, we here the process is we have averaged the terms of equation 6a to get equation 7. So, if you do the time averaging concept for the continuity equation which we have seen. So, now as we have already seen, we are transforming the, for turbulent flow we are using a mean flow component and then fluctuating component. So, if you use this time averaging concept for the continuity equation, we can write the continuity equation as del u x bar by del x plus this equation slide here plus del by del y u y bar plus del by del z u z bar is equal to 0, equation number 8. And here you can see that say as far as some of the other terms are concerned, this when we discussed, we have already discussed earlier, del by del x of u x dash bar and del by del y of u y dash bar and del by del z of u z dash bar tends to 0 when, since we take the mean component. So, now if we use this continuity equation 8 and then using this concept, the time averaging concept, we can rearrange the earlier equation number 7 in this equation into this form, equation number 9. So, finally, in x direction we can write del u x bar by del t plus u x bar into del u x bar by del x plus u y bar into del u x bar by del y plus u z bar del u x bar by del z is equal to x minus, x is the body force, x minus 1 by rho del p bar by del x plus 1 by rho del by del x sigma x dash minus rho u x dash square plus del by del y tau y x bar minus u rho u x dash u y dash bar plus del by del z tau z x bar minus rho u x dash u dash z bar. So, this is now finally the equation in x direction. So, you can see here now we have used the some of the time averaging concept, then we use the turbulence mean flow theory, and then finally we have transformed the Cauchy's equation, the general equation of motion into the turbulent flow equation. So, this similarly now we have seen in the x direction here equation number 9. So, now similar way we can write in the y direction and z direction. So, here in y direction we can write del u bar by del t plus u x bar into del u y bar by del x plus u y bar into del u y bar by del y plus u z bar into del u y bar by del z is equal to y capital Y minus 1 by rho del p bar by del y plus 1 by rho del by del x of tau x y minus rho u x dash u y dash its mean plus del by del y sigma y dash minus rho u y dash bar square plus del by del z tau z y bar minus rho u y dash u z dash bar. So, this is the equation number 10. This is the equation of motion for turbulence in y direction, and similarly in z direction we can write del u z bar by del t plus u x bar into del u z bar minus by del x plus u y bar into del u z bar by del y plus u z bar del u z bar by del z is equal to z capital Z, the body force in z direction, minus 1 by rho del p bar by del z plus 1 by rho del by del x of tau x z bar minus rho u x dash u z dash bar plus del by del y tau y z bar minus rho u y dash u z dash bar plus del by del z tau z dash minus rho u dash z square. So, this is equation number 11, the equation of motion for turbulence in z direction. So, now we have seen 3 equations in the x, y, z direction. So, these equations are called the Reynolds equations of turbulence. So, these are the fundamental basic equations of turbulence which we will be generally using to solve most of the problems. But here these equations you can see it is in terms of normal stress and shear stress. So, generally we will be transforming those equations in terms of the velocity components itself. So, that is the process which we do generally in Navier-Stokes equation. So, this process of converting we will be discussing in the chapter on Navier-Stokes equations, how we are doing this transformation. But here as far as this turbulent flow is concerned, now the basic equations here are the Reynolds equations of turbulence, equations 9, 10 and 11, as we have already seen here 9, equation number 9, 10, 11. So, these equations are called the Reynolds equation of turbulence, which are the basic fundamental equations of turbulence. So, as I mentioned, say these equations we can convert into the Navier-Stokes form by certain transformation. So, this transformation, how we transform, we will be discussing the theory, how we do the transformation when we discuss the chapter on Navier-Stokes in another separate chapter. So, here, but I will just say here we will just write this Reynolds equations of turbulence as in the form of Navier-Stokes equations of motion of turbulence as follows. So, here the 3 equations 9, 10 and 11 are converted and written like this. So, the form of equations are del u x bar by del t plus u x bar del u x bar by del x plus u y bar del u x bar by del y plus u z bar del u x bar by del z is equal to x minus 1 by rho del p bar by del x plus nu into del square u x bar. So, this nu is the kinematic viscosity. So, minus del u x dash bar square by del x plus del u x dash del y bar by del y plus del u x dash u z dash bar by del z. So, this is the Navier-Stokes form of the turbulent motion equation in x direction. So, similar way in y direction we can write del u y bar by del t plus u x bar del u y bar by del x plus u y bar del u y bar by del y plus u z bar del u y bar by del z is equal to y minus 1 by rho del p bar by del y plus nu into del square u y bar minus del u x dash u y dash bar by del x plus del u y dash bar square by del y plus del u y dash u z dash bar by del z. This is the Navier-Stokes form of the turbulence flow equation in y direction, and in z direction we can write del u z bar by del t plus u x del u z bar by del x plus u y bar del u z bar by del y plus u z bar del u z bar by del z, that is equal to z minus 1 by rho del p bar by del z plus nu del square u z bar minus del u x dash u z dash bar by del x plus del u y dash u z dash bar by del y plus del u z dash bar square by del z. So, this is the Navier-Stokes form of the equation of turbulence in z direction. So, either we can solve the Reynolds form of the turbulence equation, or we can use the Navier-Stokes form of the turbulent flow equations to get a solution. So, here now the challenge is, here you have seen that we have 4 equations, 3 equations of turbulence in x, y, z. When we consider 3-dimensional flow, x, y, z direction, we have 3 equations of motion, and then we have 1 continuity equations. So, we have 4 equations, but you can see that the number of unknown variables, even if we consider the Navier-Stokes form of the turbulent equation of motion, you can see there are 10 variables. The variables are u x bar, u y bar, u z bar, p bar, then u x dash bar square, u y dash bar square, u z dash bar square, u x dash u y dash bar, u x dash u z dash bar, u y dash u z dash bar. So, there are 10 unknowns and we have only 4 equations. So, mathematically to get a solution is very difficult, since we have got 4 equations and 10 unknowns. So, we have to go for some other theories, some other empirical relations in addition to this equation to get the solutions. The solution means the velocity components at particular time step, a particular position. If you want the velocity variations or pressure variation in turbulent flow, we can use either Reynolds equations or Navier-Stokes equation, plus we need some other relationships, since the number of unknowns are 10 and then we have got only 4 equations. And also we have already seen this root mean square represents a general way of some of the fluctuations or turbulent quantities. So, that we have already seen u x square root of u x dash bar square, u y dash bar square root of, and u square root of u z dash bar square. So, these are the root mean square values. So, generally to solve this is say to go for get a mathematical solution is very difficult. So, in the turbulence flow solution, what generally the scientists do is say they use some of the statistical theory of turbulence, say here say some of the probability aspects and some of the statistical theories are used using using the mean quantity, root mean square and correlations generally we use to get a solution in the case of turbulent flow. So, the statistical theory is one of the fundamental theory which is used in the case of turbulent flow solutions. So, solutions means we want to find out the velocity components and pressure components at any particular time step and at any particular point which we consider. So, this root mean square values represent the intensities of turbulence, as we have already seen. So, the statistical theory based upon the correlations or the RMS or the mean quantity we can utilize. So, we have already seen the intensity of turbulence is expressed as E is equal to square root of 1 by 3 u x dash bar square u y dash bar square plus u z dash square by u 0, where u 0 is the mean the free stream velocity, and say these quantities like u x dash u y dash bar, u x dash u z dash bar, u y dash u z dash bar. So, these quantities are called cross correlations. These quantities are called cross correlations. So, what we do to, as I mentioned, in turbulent flow the solution is very difficult, since the variations say we have got so many unknowns, and then we have got only few equations. So, generally use the theory statistical theory. So, there we use this mean flow, mean components, then RMS and then the cross correlations. So, these cross correlations, as we have seen in the previous slide here, these are called cross correlations. So, these cross correlations represent additional shear stresses due to turbulence. So, here this slide you can see here in this slide shows say additional shear stresses will be generated due to turbulence, and this cross correlation represents these additional shear stresses, and these quantities can be measured by hot wire or hot film anemometer for some of the solutions. So, here this slide shows the additional stresses like u x dash square bar square or u y dash bar square or u z dash bar square or u x dash u y dash or u x u z dash bar or u y dash u z bar. These are all the apparent or turbulent or Reynolds stresses, as we have seen. So, If some of the components we can measure using some of the equipments like the hot filling anemometer or some of these, and then these measured values we can utilize in some of the equations to get the solution. So, here you can see in this slide, say if you plot y by delta, that where delta is the boundary layer thickness for a particular problem, y by delta versus u x bar by u 0, where u 0 is the free stream velocity, then you can see its variation for u x dash u y dash bar by u 0 square, this it varies like this, and then the mean square RMS value varies like this. So, this say some of the components we can measure, and some of the then we can use some of the empirical relationship, and then also we can use the basic equations to get some of the solutions. So, as a mathematically, since we cannot get a solution directly, so that is why we go for this kinds of approach in turbulent flow theory. And then we can see here the Reynolds stresses are caused by turbulent fluctuations, as we have already seen, given by the time average values of the quadratic terms in turbulent components. So, caused by eddy viscosity. So, we can represent this u x dash u y dash term say by eta into du x bar by dy, where eta is the eddy viscosity. So, this we can utilize the eddy, say some of this relationship like u x dash by u y dash is equal to eta du x bar by dy. So, this is another important relationship we use in the turbulence solutions. So, now see the turbulence model. So, as I mentioned, the problem is to find out the various velocity components in x, y, z directions and the pressure components. So, the difficulties, as we have seen, generally the governing equations are only 4, and there we have got 10 unknowns, and then we cannot get a mathematical solution directly. So, generally what we go for is a closed solution or closed soluble set is generated. It is the process of averaging losses. Say in the process of solution, some of the information will be lost. So, the lost information like the stresses, as we have seen the Reynolds stresses, some of this will be lost, and the lost information must be gain back through some other relationship. So, that is what we do in this turbulence models. So, this way of approach is called closure problems in turbulence modeling or turbulence solutions, where when we use say some of the basic equations like Navier-Stokes form of the equations, and then some of the important informations are lost, and this we gain back by some other relations. So, this procedure is called closure problems, and solution of closure problems are through that we get the present the turbulence models. So, the solutions of closure problems through this we get the turbulence models. So, as far as turbulence models are concerned, if you refer to literature, we can see 5 types of models. First one is called zero equation models. So, in this zero equation models, what we do is, this is the process of modeling using only the instantaneous Navier-Stokes equations, but we do not use any direct turbulence differential equations. Generally, this is achieved through eddy viscosity and mixing length concept. So, this is the first approach. So, generally in literature there are 5 types of turbulence models. So, first one is the zero equation models. In zero equation model is based upon the eddy viscosity and the mixing length concept. So, here we do not directly use the turbulence differential equation, but we use the eddy viscosity and the mixing length concept. So, this is the approach called zero equation model. And second turbulent model is called one equation model. So, here models we use the turbulence kinetic energy. So, instead of the directly using the differential equation, we use the turbulence kinetic energy to get a solution for velocity or pressure variations. And the third kinds of models are called the two equation models. So, here in two equation models, what we do, this model is using one differential equation involving the turbulence velocity scale and other differential equation involving a turbulence length scale. So, this is the third kinds of models, which is called two equation model. So, here we use one differential equation and other differential equation involving turbulence length scale. And the fourth kinds of equation model is called a stress equation model. So, here the models involving differential equations of all components of the Reynolds stress tensor and a length scale. So, this is called a stress equation models, where we use all the differential equations and components of the Reynolds stress tensor and length scale. And finally, one of the last 2 decades, another development in turbulence modeling is called a large eddy simulation. So, here what we do, these models involving calculation of the 3-dimensional eddy structure plus a model for small scale turbulence. So, this is what we generally do. In the fifth model, it is called a large eddy simulation model. So, in 3 dimensions we will be using the 3-dimensional eddy structure. That means, as we have already seen, eddies will be formed and an eddy structure is used, and then plus we use a small scale turbulence to capture the turbulence fluctuations. So, that is so called a large eddy simulation. So, in literature we can see 5 kinds of models. First one is the 0 equation model, second one is called 1 equation model, third one is called a 2 equation model, and the fourth one is called a stress equation model, and fifth one is called a large eddy simulation model. So, due to all these complexities, we will not be discussing further all these models, but we will be discussing only some of the 0 equation model concept like mixing length and other things in the following lectures for the turbulence flow simulations in channels and pipes. Since other models involves a lot of mathematics and a lot of complexities, so we will not be discussing the other 4 models. We will be discussing next the mixing length theory and related concepts.